Good morning. My name is Anirvan Gupta and I am currently working as an assistant professor of physics at the JSPN University, Pune. I come from a simple middle class Indian family where education is regarded as the greatest wealth one could ever possess. My father was a chemistry graduate from the University of Calcutta and one of the pioneers of colored glass technology in India. My mother from the University of Calcutta is an arts graduate and she practices music. From them, I have learned humility, discipline and respect for learning. My wife is also a teacher and we try to nurture curiosity in our two children. My schooling began at St. Xavier School, Panchkula near Chandigarh, while my higher education from BSc to PhD was completed under the University of Pune. During my doctoral work, I had the opportunity to briefly work with Professor Adam Hardy at Cardiff University, Wales, before completing my PhD under the guidance of my guru, Professor Dr. Rai Bakkar sir. Interestingly, my father always wanted me to become a mechanical engineer. Unfortunately, he passed away before seeing my higher secondary results. Admission to a government college in science introduced me to physics, almost by chance. But that unexpected turn became the defining journey of my life today. Before becoming a successful academician or researcher, I wish to become a good human being. A verse from the Bhagavad Gita has always inspired me. Nahi jnanena sadrishyam pavitramiha vidyate. To me, knowledge is meaningful only when it develops humility, compassion, and a sense of responsibility towards the society, towards the family. This philosophy naturally shapes my teaching. I do not see education as preparing students merely to reproduce information or results in examinations. I believe a physics classroom should encourage students to observe carefully, to experiment, to reason scientifically, and to question. Conceptual understanding remains time invariant, while applications and technologies continue to evolve. My own research has similarly evolved, from acoustics and sound heritage to computational modeling and more recently quantum technologies. Whatever I learn through research, I try to bring back to the undergraduate classroom through low-cost experiments, computational tools, and interdisciplinary learning. Alongside teaching, I shoulder several other academic and non-academic responsibilities within my university. This certainly makes life busier, and sometimes sleep is only a luxury. But I willingly accept these challenges because each responsibility contributes to building a better academic environment for my own students. My association with the Indian Association of Physics Teachers has been undoubtedly one of the most enriching experiences of my professional life. As I had heard from my gurus, IAPT has reaffirmed my belief that physics education is not merely about teaching a subject, it is about nurturing academic temperament, nurturing curiosity and integrity. I believe physics education advances when teachers are given freedom to innovate. Students are trusted with meaningful work and research from the first year itself. And institutions build strong partnerships with research organizations and laboratories, industries and professional bodies. Personally, I wish to continue learning and experimenting with new teaching approaches every day. Institutionally, I am striving to create a culture where experimentation and social relevance becomes an integral part of undergraduate physics education. Over the past few years, I have tried to ensure that my contribution extends beyond my own classroom. My efforts have largely focused on creating better learning opportunities for undergraduate physics students and at the same time strengthening the overall ecosystem of physics education. One of the major areas of my work has been curriculum development and modernization. As a member of the Board of Studies in Physics at JSPM University, Pune, I have contributed towards introducing contemporary topics in physics in our curriculum, such as computational physics, quantum technologies, Python programming, AI-assisted learning, and semiconductor technologies within the undergraduate physics curriculum, while ensuring that these additions continue to strengthen the conceptual foundations of physics. I have also had the opportunity to serve on the curriculum development committees of few other institutions. Very recently, I got an opportunity to contribute to designing and implementing a mandatory quantum physics theory and laboratory course for the first year engineering students as well. I strongly believe that students should have access to modern experimental tools from the beginning of their undergraduate education. With this objective in mind, I have worked towards introducing computer interfaced physics experiments using XSpice and very recently the SEELab 3.0. We have also introduced FIFOX-based activities in our laboratories. These initiatives allow students to acquire real-time data, compare experimental observations with computational simulations, and something that they already do in the physical laboratories. They also appreciate the relationship between theory, experiment, and numerical modeling. Another area that I consider extremely important today is creating opportunities beyond the classroom and beyond the institute. During the last few years, I had the opportunity of personally mentoring around 70 first-year undergraduate physics students through structured summer internships and research-oriented activities. Several of these students were placed for internships at elite institutions such as the IISER Pune, Kalpakkar in Pune, the Science Center in Pune, and neighboring industries, enabling them to experience research and professional environments at a very early stage of their academic journey. Interestingly, a few students also secured paid industrial internships or apprenticeship with monthly stipends ranging up to 18,000 per month, which I consider a wonderful encouragement for the first year undergraduate physics students. I have also tried to build strong academic collaborations that directly benefit this undergraduate physics education. Over the years, I have worked closely with institutions and organizations like the IISER Pune, CDAC in Pune, of course our own IAPT, the ARAI Pune, and international collaborations such as the UPM Madrid in Spain. These interactions have enabled me to bring in experts, with them new ideas and emerging technologies into the undergraduate physics learning environment. Recognizing the growing importance of quantum technology today, I have been working to establish a structured educational framework for quantum education at the undergraduate level in our institute. I am currently leading a university-supported major project on developing a quantum education and experimental learning framework for undergraduate students and have also submitted a proposal under the DST National Quantum Mission for establishing a dedicated undergraduate quantum teaching laboratory in our university, which will benefit the neighboring institutes as well. These initiatives aim to ensure that students from conventional undergraduate institutions also receive exposure to one of the most rapidly advancing areas of physics. Beyond curriculum and laboratories, I have always believed in building academic communities. I recently conceptualized and established, after approval, an IAPT student chapter at JSPM University of Pune as a nodal center to provide students with regular interactions with physicists, researchers, and educators from across the country. I have also been associated with IAPT for many years, including serving as the National Graduate Physics Examination Coordinator for the Dadra and Nagar Haveli Union Territory region for 7 long years and contributing to the recently launched EnQuest initiative for quantum science education in our country. Faculty development and student development programs has been another important part of my work. I have organized several FDPs and STTPs, workshops and seminars on experimental physics, quantum technologies very recently, and emerging teaching methodologies. One such week-long national FDP with international participants on quantum computing and technologies brought together faculty members, research scholars, and industry professionals from across India, creating a collaborative platform for strengthening undergraduate physics education. Finally, I believe that learning should remain accessible to every student. And with this objective, I am voluntarily contributing to the localization of the FIFOX application developed at RWTH Aachen University, Germany, into Indian regional language, making smartphone-based physics experiments more accessible to students from diverse linguistic backgrounds in India. All these initiatives, taken together, have been guided by a single objective: to create an undergraduate learning environment where students not only understand physics but also experience it. Understood? So we have seen that temperature dependence or okay. Now let us verify that. Let us read that. Okay. ये diagram आपको दिख रहा है सबको? Can you see that, right? We have already shown. So let us read that. So कैसे hit करेंगे? Let me use this. Hopefully connections are still there. हम इसको थोड़ा सा heat करते हैं. आग लगा देंगे. ठीक है? So we have heated it. Now let us see. So this was your earlier response. Let us see if we can verify. We have studied in theory, right? So whenever you are supplying some heat energy, what is happening? We have seen in the theory, and this is something that we have verified. So as the temperature increases, what is happening? What is happening? आपका जो threshold है, is getting going towards the voltage. So ये कम होगा, ठीक है? Like that, this is something that we have seen. Now we do a simple another experiment. Remove this diode, and let us see if physics works. So what we will do is, instead of the diode, we will replace it with a LED. What is an LED? Light emitting. Light emitting. Very good. So we are using the same connection. We are using the same connection that we had used earlier. So in this connection, what we are doing? We are simply replacing this diode with a LED. That is all we have done. Now I want to show you what is the LED that we are using. What color is LED? So LED, because it is a semiconducting material, will it instantaneously give current if you give some voltage to it? Current instantaneous बढ़ेगा? Instantaneous बढ़ेगा? Diode में क्या हुआ था? Instantaneous बढ़ा था? The voltage you increase, the current initially remains 0, and then at the threshold it increases. Let us expect the same to this diode. So let us again run this and let us see. So what you are observing, is the current increasing? Yes. Linearly? Is it linear? It is not linear. Why? Because LED basically is a semiconductor diode. So the IV characteristics are more non-linear. It goes towards non-linear. Okay? Now let us write. Now forget about this LED and all that. Can somebody tell me what is the threshold voltage? यहाँ पे दिख रहा है आप लोगों को? I'm sorry, ये बाहर थोड़ा प्रॉब्लम है. Threshold voltage कितना दिख रहा है? If I do that, let us assume it is somewhere around 1.75 something. Okay, let us write that. Okay, I write it here. I hope that is visible. So your threshold voltage is around 1.7. Let us write 1.8 for threshold voltage is 1.8 volts. Okay. Now we do not know what is the color of this LED. Let us try to use physics principles and laws and find out what is the color of the LED. So हम prediction करेंगे. Write some laws of physics. Okay. What is the equation which gives you the electrical energy that the electron is giving? What is electrical energy? E equal to E into V. This is the electrical energy. Can you see that? E into V. So what is the charge of an electron? 1.6 into 10 raised to minus 19 coulomb. Let us substitute this voltage that we are getting. Let us remember this. So we substitute 1.8 volts. And tell me what is the result? What is the result? Calculator लगेगा? Why do you need a calculator? 16 into 18 कितना होता है? अरे बेसिक मैथ्स सिखाऊं अभी. 16 into 18 okay, 2.888, right? 2.88 into 10 raised to minus 19 joule, because that is energy. Now, if the electron is giving away this energy, energy, what will happen in a LED? Electron, suppose the electron is here, now conduction band is a high energy state, valence band is a low energy state, right? The electron is in the conduction band now. So now nature always prefers the systems to come to the lower energy states, we have seen that. So electron eventually will jump down to the valence band and in the process it will release this energy. Law of conservation of energy क्या बोलते हैं? Energy cannot be, it cannot disappear. It has to be converted to something. So when it will be converted, this energy will be converted in the form of some light. Okay? So that is your photon, h into nu. So अगर हम E equal to h into nu, this energy is converted into photon energy. Then can you find out the frequency of that photon? It will be E upon h. It will be E upon h. Can you do that? If I substitute this 2.88 into 10 raised to minus 19 joule divided by what is h? Remember? And if you don't remember, ये एक्सपेरिमेंट करके h भी निकाल सकते हैं, मैं 2 मिनट में बाद में बता दूंगा, बट यू विल डू दैट. -34 जूल सेकेंड. कैन यू फाइंड आउट व्हाट इज न्यू? इसमें 3 into 10 raised to power 14 per second. That is hertz basically. Let us write it per second. Now we have the energy, now we have the frequency. Can you tell the color of the LED through frequency now? You need wavelength. Wavelength कैसे मिलेगा? Do you know any formula which relates frequency and wavelength? You know C equal to nu into lambda. So lambda will be C upon nu. C you know 3 into 10 raised to 8 meter per second divided by 4.3 into 10 raised to 14. So 0.69 something. कुछ तो है. Let us write 690 something into 10 raised to minus 6 meter. That means approximately, let us write 690 nanometer. Now you know the wavelength of light. ये भी रखा है मैंने, ये आप लोगों को तो याद होगा, मुझे गारंटी है. Yes sir. 690 nanometer corresponds to somewhere around 700. That is your red color. That means from our calculations electrical energy निकाला हमने, electrical energy निकाला. Planck's equation से we have found out what is frequency and ultimately we have found out the wavelength and we assume that and we predict that the light should be red color. कौन सा कलर है? So basically what we are doing is technology replacing physics? No. Rather, technology is only helping to understand physics more accurately. समझ में आया? So these are all the processes. I'll show you something different. और ये क्यों हो रहा है by the way? क्यों हो रहा है ये? इलेक्ट्रॉन यहाँ पे था इलेक्ट्रॉन. इलेक्ट्रॉन क्या किया? हमने यहीं पे डिस्कस किया. इलेक्ट्रॉन jumps back. So in the process what happens? The electron releases some energy. That energy is emitted in the form of a photon. The photon has its energy. What would be the energy of the photon basically? The energy of the photon will be difference between the bottom of the conduction band and the top of the valence band. That is the energy gap. And that is why in text you will find this Eg is given as the energy of the photon. Rather it can be approximately. Why approximately? क्योंकि जरूरी नहीं है photon यहाँ से यहाँ भी है. Photon यहाँ भी हो सकता है. It is all about like inter-school and intra-school events. Intra-school मतलब आप पहले आपस में खेलते हो, फिर इंटर-स्कूल यानी दूर जंप करते हो कहीं पे. सीढ़ी के ऊपर से सीढ़ी के नीचे तक आने के लिए एक स्टेप आते हो. You do not directly jump from the top to the bottom, right? So similarly, when the electron is there, what is the conduction band we had seen? Band का मतलब क्या है? Band का मतलब there are discrete energy levels, allowed energy states which are very closely spaced. So even in those energy states, when the electron is in the conduction band, it can collide with the lattice, with other charge carriers. In that process, it can lose part of its kinetic energy. That kinetic energy is liberated in the form of heat already. So electron जब यहाँ पे है,
यहाँ पे भी वो कहीं कहीं इधर उधर नीचे नीचे जंप कर सकता है. So eventually छोटे छोटे steps लेके इलेक्ट्रॉन यहाँ पे पहुँच जाता है. Electron will reach to the bottom of the conduction line, and then the electron will jump here. Similarly, because holes can also move up to the top of the valence band, and the difference is generally Eg. But that is not, the case every time. There may be some arbitrary electron which jumps from another level to another. So इसीलिए जब भी आप मार्केट में एलईडी खरीदने जाओगे आपको स्पेसिफिक वेवलेंथ का एलईडी नहीं मिलता है. देयर विल बी अ बैंड ऑफ वेवलेंथ, एक रेंज ऑफ वेवलेंथ, व्हिच इज कॉल्ड एज, याद है टर्म, इट इज कॉल्ड एज द एमिशन स्पेक्ट्रा. यू गेट अ कर्व लाइक दिस. तो एक डोमिनेंट आपको मिलता है, एक डोमिनेंट होता है, उसके बाजू में छोटा सा है, इतना ब्रॉड भी नहीं, पतला सा. ठीक है, दैट इज व्हाट. ओके, वन मोर थिंग आई विल शो यू. तो ये सब आप पढ़ो. एक रिसर्च पेपर है, मैं आपको बाद में भेजूंगा, उसमें इसका पूरा है. नाउ आई सिंपली रिप्लेस दिस एलईडी. मेरे पास एक और रेड एलईडी है. आई रिप्लेस दिस. मैं ये एलईडी निकाल देता हूँ और उसके जगह ये दूसरा एलईडी लगाता हूँ. ओके, एंड आई स्टार्ट इट. ग्रीन लाइन दिख रहा है. व्हाट यू ऑब्जर्व आइडियली, रेड रेड है तो एक ही साथ जाएगा. बट if I zoom this now, see, this is very interesting. If I zoom this, overlap हो रहा है क्या? No. Exact overlap है? नहीं है. क्यों नहीं है? दोनों रेड है, तो ओवरलैप क्यों नहीं हो रहा है दोनों में? ये देखो, कंपनी के हिसाब से. आई डोंट नो, एलईडी देख के कंपनी में नहीं समझता है. ठीक है, दिस इज समथिंग दैट यू विल फाइंड आउट. हर चीज क्लास में आंसर नहीं होगा. दिस इज समथिंग दैट यू विल फाइंड. ओके, मैंने एक और चीज छोटा सा बोला था. सपोज मैं अभी ये रेड की जगह येलो एलईडी लगाता हूँ, कनेक्शन भी सेम ही रहता है. येलो एलईडी लगाएंगे, जो मैंने आपको प्रॉमिस किया था, हम देखेंगे 1 मिनट में. येलो एलईडी लगाते हैं, स्टार्ट करते हैं. ऑफ कोर्स उसका ग्राफ आपको अलग मिलेगा, कैरेक्टरिस्टिक्स अलग मिलेगा. अब येलो भी निकाल दो और ग्रीन सपोज. अब आप मुझे बताओ, अब मुझे सपोज h, जैसे आप लोगों को h का वैल्यू याद नहीं था, नथिंग रॉन्ग, इसमें से निकाल सकते हैं क्या? कैन यू फाइंड आउट व्हाट इज द वैल्यू ऑफ h फ्रॉम दिस एक्सपेरिमेंट और ग्राफ इटसेल्फ? ओके, समटाइम्स वी फॉरगेट. क्या पता 6.626 क्या एक और ग्राफ आ गया. कैन यू फाइंड आउट व्हाट इज द वैल्यू ऑफ h? यूज द सेम फॉर्मूला. h कहां से निकलेगा? गो रिवर्स. सो हमने लिखा था h यहाँ पे है, equal to h nu. Now I want to find out what is h. You equate these two. So I'll write nu lambda. I'll write this here. Nu lambda equal to h. Sorry. E equal to h nu. E equal to h nu will be equal to E into VTH. This is your threshold voltage. तो इसमें से आप h कैसे निकाल सकते हैं? E तो कांस्टेंट है, E is constant. So if I have h equal to VTH upon nu into E, E is a constant. That means if from this experiment I can determine VTH, using the value of VTH I can determine what is nu in the same process. And if I plot a graph of VTH versus nu, I will get a straight line. If I find out the slope of that straight line, I will get what is the value of VTH upon nu. I substitute it. I already know the value of E. I can find what is the value of H. So experimentally, आप थ्योरी के फॉर्मूले अगर आपको पता है, फिजिक्स के फॉर्मूला, एक्सपेरिमेंटल अगर आप करोगे, आप अननोन कांस्टेंट्स भी ऐसे निकाल सकते हैं. So you have to think that कैसे निकालें, नहीं आता. So this is all.
The achievement that gives me the greatest satisfaction is seeing undergraduate students transform from passive learners into confident young researchers. Several of my former students have pursued higher education at elite institutions like the IISER Pune, IIT Guwahati and the University of Pune, while others have established successful careers in either research or industries and even scientific publishing like Springer Nature. I have also facilitated paid summer internships opportunities to first year BSc Physics students. Watching students discover their own inner potential has been far more rewarding than any personal recognition so far. I strongly advocate introducing students to socially relevant research from the very first year of their undergraduate education. Accordingly, my students have actively participated in research conventions like the Avishkar, organized by University of Pune. One group of my first year students have also investigated the physiochemical characteristics of nearby water bodies using ultrasonic interferometers available in our first year labs. And the resulting work has also been communicated to a peer-reviewed journal now. Another group of my students from first year is presently developing a computational model for intelligent electrical power distribution across interconnected networks, inspired by the recent developments in AI-assisted power management. And this project integrates physics and optimization while encouraging students to apply scientific thinking to real societal challenges. The project is also inspired by an industry project. I was appointed as the PhD coordinator, member of the Board of Studies, School Research Committee, SRC, and the Research Advisory Committees at my university. I have also contributed to curriculum development as the CDC member of other institutes by introducing quantum technology, quantum physics, and quantum physics laboratory courses. I have established the IAPT student chapter at JSPM University Pune, and I am also presently leading the development of a quantum educational experimental learning framework in collaboration with SEELab Pune. I also serve as the principal investigator for the proposed quantum undergraduate quantum technology teaching laboratory under the DST National Quantum Mission. My research has expanded from acoustics to quantum technologies while remaining very closely connected with teaching. I am presently involved in collaborative research on heritage acoustics, virtual acoustic reality, quantum computing, applications in acoustics, advanced materials and medical physics through collaborations. Collaborations with institutions including CDAC Pune, ARAI Pune, GB Acoustic Bangalore, Alpha Acoustic Pune, UBM Spain Madrid, and clinical partners. I have authored 6 book chapters on emerging areas of physics and technology, believing that research should continuously enrich undergraduate teaching and learning. I have also been fortunate to contribute beyond my own institution. As the convener of National Faculty Development Program on Quantum Computing and Technologies, organized jointly with SEELab Pune and IAPT, I had the opportunity to interact with educators and researchers across the world. My continuing work in quantum education today has led me to be appointed as the National Co-Coordinator of the IAPT National Network of Quantum Engineering, Science and Technology, NQuest. I also serve as an external expert and panel member for recruitment of project engineers in quantum technology at SEELab since past 2 sessions of interviews. Contributing through this, I contribute from the academic perspective to a national research organization. My work has received encouragement through recognitions such as the JSPM University JSPM Group Academic Excellence Award on 2 consecutive years, the STEM Educator Excellence Award from ISER Pune and Tata Technologies, the IBM Quantum Scholarship for an entire year, Best Scientific Paper Award at conferences, and recognition in the Avishkar Research Competition in both doctoral and teachers categories. I have also had the opportunity to serve as the principal acoustic consultant for Z Media's documentation on the Temple of 84 Bells in Noida. This has demonstrated how physics can contribute to understanding and preserving India's glorious scientific and cultural heritage. However, if I were ever asked what I consider as my greatest achievement, my answer would remain unchanged. It is the moment when one of my former students returns years later and says, "Sir, I remember that experiment," or "I remember the discussion changed the way I think." For me, that is the highest recognition a teacher can ever receive.